the talkie shop. Jessie and I are now going to talk about stuff that's not just statistical and impenetrable. Well, I mean, maybe her talk will include that. We'll find out soon. But folks, we have a very special speaker with us today. We've got Jessie Oehrlein, class of 2016 from Olin, and now assistant professor at Fitchburg.
That's correct.
And so could you tell us a little bit about the institution that you're currently at?
Yeah, so I'm at Fitchburg State University, which serves North Central Massachusetts in our state college system. So pretty regional, public, lots of commuters, non-traditional students. So I've really enjoyed being there the past year and a half.
Very cool. Okay, so this is like year 2 on the job.
This is year 2.
Wow. Okay, so how's it been?
Better this year than last year.
Okay. I feel that.
Yeah, definitely getting used to how things work.
And so, in terms of the work that you're doing now, I know we had talked ages ago about what you do. I guess your application space is weather, but like, how do you approach all of this? Because you teach statistics. It seems like you do stuff more in like the inference and modeling side of things. How do you think about the kind of work that you do?
Yeah, I guess I would say I kind of exist across some academic spaces, not necessarily as someone who is bringing those fields together, but as someone who's hopping across them. So as an educator, I consider myself very much a statistics educator.
Mm-hmm.
As a researcher, I'm pretty solidly an atmospheric scientist, right? And I'm bringing some care about the statistics and mathematics to that. But I do what looks like pretty standard atmospheric science work.
Okay, so you're pretty solidly within that specific discipline.
Yeah.
Okay, cool. And what got you into this? Because I remember, like, you ran the Midnight Math Club when you were here.
Yes.
And so you're very much into mathematics. But how did that journey land you in atmospheric science?
Yeah, so I'm actually going to say a little bit about that
I don't want to
in
say
the talk.
So.
Thunder, good one.
A lot of fun.
But it was basically finding the pieces of what I had enjoyed from experiences leading up to grad school and finding the field that best let me put them together.
Okay, cool. It sounds like a natural segue to what you're about to talk about. So I'll yield the floor.
Okay, thank you all for being here right before finals start. So I'm going to try to tell you how we know what we know in atmospheric science, and like we just said, a little bit of how I ended up in this field in the first place. I guess as extra context, I was a mechanical engineering major at Olin, and like Zach said, I did a lot of math, so it wasn't really obvious to folks that this is where I would end up. So when I tell people that I'm an atmospheric scientist, they generally think of one of two things. Either all the way over here on the weather scale of things, or on the other end of the possible time scales with climate change. All right, so if we start with weather, we're talking about the state of the atmosphere right now, out to maybe about 2 weeks from now. And the information we need to predict the weather is really the current state of things. You know, this is how cold it currently is in Needham, and how cold it currently is in Fitchburg, and then we can use our understanding of the physics of the atmosphere to propagate that forward. But at some point that stops working, right? And you probably have intuition for this, right? That you can't really trust a weather forecast a month out, or that the way weather is right now today doesn't tell us how things will be in 50 years. But there are a lot of at least simple mathematical models of physical systems where we would be able to do that. We would be able to say, this is where we are now, just run my time out for 50 years, and I should know where we end up. So something must be breaking that in the atmosphere. And it's the fact that it's a really nonlinear system. This means is that if you start with kind of the state of things right now, and just a little bit apart from that, right, just measurement error on our instruments, really quickly the trajectories of what happened are going to diverge a lot. And that's known as it being a chaotic system. This up here is a chaotic attractor, in particular for the Lorentz 63 equations. These are named after Edward Lorenz, who was studying the atmosphere. He was trying to come up with a simple model of atmospheric convection, basically how storms bubble up. And he and the woman doing his computing for him at the time, Ellen Fetter, found that if they just made rounding errors when they tried to rerun their simulations, they got really dramatically different results. So we figured out, basically in the 60s, that our simplest reasonable models of weather were pretty chaotic. That means our information for when we're trying to understand climate change has to be coming from a different place. Right? It can't be about initial conditions anymore. So instead of being an initial value problem, it's what we call a boundary value problem. It means that our information is coming from things like human emissions, the interaction of the atmosphere with the ocean, and the land and the ice. So that's how we figure out things about climate change. It's also how we learn about a lot of the stuff in the middle of these two extremes. And I actually work in the middle. I'm mainly in the subseasonal and seasonal variability space from about 2 weeks from now to 6 months from now. Where at the beginning we can get a little of information from initial conditions, and then we mostly need boundary conditions beyond that. But despite the fact that we have this huge range of timescales that are really different kinds of problems in some sense, the tools we use across this range are remarkably similar. In the same way, even though we're looking at a huge range of spatial scales, we can still end up using similar tools, right? They look a little different if I'm trying to model tornadoes that happen at a very small scale, or the jet streams that happen at a planetary scale, but they're still the same 3 basic tools in the toolbox. Those are observations, theory, and models. Right, so observations is looking at what actually happens. Weather balloons, weather stations, ships, buoys, planes. Satellites are a really important one for me. You could also put things like traditional ecological knowledge in this category, right? What has actually happened? Theory is us trying to wrap our head around conceptually what's going on, or really simple mathematical models, right? Schematics, things we can solve by hand. What's the most basic level of how we think things should work? Right? And then when atmospheric scientists say models, we don't mean this in the mathematical modeling sense, right, which would also include theory. We mean it in the big computer model sense. So this is talking about kind of discretizing, splitting up into grid cells, a region, maybe even the whole globe, like in this picture, and having this complicated system of equations that we couldn't really solve by hand, run over potentially hundreds of years in our model to see what happens. So to say more about each of these, I'm going to talk about basically 2 cases. The first one is a question that comes up basically every summer and fall, which was, does climate change affect hurricanes and other tropical cyclones? And if so, how? Right, so this is a climate change timescale and what we call a synoptic spatial scale, looking at basically thousands of kilometers. The other case I'll look at is what I study, the stratospheric polar vortex. So this is a seasonal timescale and a synoptic to planetary spatial scale, so quite big in a spatial sense. So I guess a note about that, the term polar vortex might be familiar. You'll sometimes hear meteorologists say it. When they talk about it, they're generally talking about this lower red polar vortex, which is really just the jet stream getting extra wavy, right? So if you've heard about like cold coming down from the Arctic, it's the polar vortex. That's what that is. I'm talking about a feature higher up that forms basically every winter. I'll say a little more about that later. But just kind of as a reminder, we're talking about this higher up object. Okay. But how did I get here in the first place? So I grew up in Oklahoma. This is a map of the average number of tornado days per year over the course of about half a century. And I lived right there. So right at the edge of that dark purple splotch. And in fact, probably in my first 10 or so memories, is the first time the National Weather Service ever issued a tornado emergency. This storm, tornadoes right here, on May 3rd, 1999, hit what would eventually be my high school, came pretty close to my house. So I grew up around severe weather. It was something I had a fairly low-key but consistent interest in. But I wanted to be an engineer. So I ended up here in the mechanical engineering program, where I did things like take mod sim and fall in love with mathematical modeling, take PDEs, be like, oh, I can use math to figure out how fluids and heat work. This is cool. Take transport, which was more on the fluid dynamics and the heat transfer. I was like, ooh, the fluids here, especially cool. And then take thermodynamics, right, about the movement of heat and energy and how they work. And those were the pieces from mechanical engineering that I really liked and wanted to keep doing in some sense, even as I figured out that maybe engineering wasn't quite what I wanted. So I was looking for another field that would include all of these things. And I found my way through looking for grad programs to atmospheric science. And so this picture that I pointed to at the top for thermodynamics is a Carnot cycle, which is kind of our ideal heat engine cycle, but it's using the Carnot cycle to try to explain a hurricane. So all of these ideas, instead of doing them in pipes or heat exchangers, now I'm getting to think about them in this different, thin, rotating layer of fluid that is our atmosphere. So to take the hurricane transition, the main question here is, how does climate change affect tropical cyclones? And so here we're looking just at the North Atlantic basin. So the area of tropical cyclones that most affects the US. And the place where maybe it's natural to start on this question is to say, okay, we can see how many there are over a long time, right? We've been keeping track of tropical storms and hurricanes for more than a century. So we can just graph how many there are and then put a smoothed curve in, right? Because you can see it's pretty noisy. And it certainly looks like in this graph there's been an increase over time. There's a problem with this though, and that's that our observations have gotten a lot better over the past 50 or so years, mainly because of satellites, but even before that. So for example, anything that wasn't landfalling or didn't happen to bother a ship, right, we wouldn't have seen here. This meant you were missing a lot of weak systems and a lot of short-lived systems especially, but probably not exclusively those. So we can kind of try to correct this graph. We can say, okay, let's only look at the ones that are long-lived enough. Let's try to add in what we think is probably missing from the early period, right? So there's some modeling going into adjusting these observations. And now, it doesn't so much look like there's an increase. Maybe still over the past 50 years, but there's not a clear signal here. That's about as far as we can get on this question out of the observations. So what do we do instead? And this is a place where turning to models is really helpful. Because with a model, we don't just have one instance of the year 2000, right? I can keep running things under conditions that look like 2000 over and over and over. I can reach in and fiddle knobs and do experiments in ways that I can't with the real atmosphere. So the way these kinds of models are set up, they're called Earth system models, is we have pieces for each part of the Earth system. So we have an atmosphere general circulation model, right, showing everything that's happening in the atmosphere. Same for the ocean and the land and the ice. And then they all talk to each other through a central coupler. And that central coupler means that I can fiddle with the atmosphere without worrying directly about how that's going to affect the ocean. It just has to be able to talk to the coupler. So I can switch pieces out really easily. It's very modular. Within each of these, we have something that looks like this. So this is the atmosphere in particular, right? We put a grid over the Earth. We do it vertically as well. And within each kind of grid box, we're calculating some variables, right? Temperature, wind, pressure. And then we're using partial differential equations that say how things change in space and time. To say, at the next time step, how will this grid cell affect all of its neighboring grid cells in every direction? And how will they affect it? And so there's a lot of math kind of hidden in this piece, right? Both in the governing equations that we use, which are mostly but not entirely agreed on by folks, and also in how we optimally do the numerics for this, right? What's the right shape for splitting this up into a grid? What are the right methods for how these cells talk to each other? And then there are some things that are too small for us to do in kind of this overarching way. Right? There are some things that we kind of have to calculate inside each cell on its own. And that's where a lot of our uncertainty comes from. So you'll hear climate modelers talk about the big picture, the PDEs about how things talk to each other as the dynamics, and the things that we kind of have to specify within each grid cell as the physics, or the parameterization. Okay, so here, back to our tropical cyclone question. How can a model like this help us? We can say, well, let me reset things in the atmosphere, and maybe in the ocean as well, so that they look like 1850, which is our standard kind of for human-caused climate change, right? And then I can run that simulation for 200 years of model time. See how many Atlantic hurricanes I get on average, right? Then I can say, okay, what about year 2000 conditions? What about predicted year 2100 conditions, right? And try to really isolate, at least in model land, the effect of how things have changed over this time period. So what does this end up telling us? In models, in terms of number of storms, we get results all over the place. Right? Some models say we should expect more storms, some say we should expect fewer, some say no change. Observations are roughly along the same lines. So here, consensus right now is we don't have evidence of any change. It's pretty unclear what's happening. But a lot of other aspects are quite clear. In terms of how strong storms will be, theory of sort of what gives tropical cyclones strength, along with models, say that we should expect stronger storms on average. And in observations, we're starting to see that. For rainfall and storm surge, things are pretty clear at this point. We're seeing storms rain more, we're seeing higher surge. So in terms of impacts, right, those are going up, which in some sense means that number and even strength don't matter so much, right? This is the thing that most matters to people. And then sometimes we're making our hypotheses from observations. So something we've started to see in observations is that it seems like storms are starting to get stronger faster. That's this rapid intensification. And also that they are physically slowing down. right? That the translation of storms is getting slower. So this is about 5 years ago now, but when Hurricane Harvey hit Houston, basically got there and sat for days, right? And rained 51 inches of rain on the city. Right? And some of that is increasing rainfall amounts, but some of it is this slowdown, that it just wasn't moving. So we have some evidence for this in observations. We're really just starting to look at this in models and to think about what theory might tell us, if anything, about these. So that's how those three are working together for that question. Okay. And I guess one last place this naturally leads that people ask is, was this particular event caused by climate change? Something that we can't really answer with a definitive yes or no. But what's developed is a field called attribution that says, okay, we can't say this event was caused by climate change, but we can say a storm that rains this much is 50% more likely now than it was in 1850. This was developed first for a European heat wave in the early 2000s. That was pretty deadly, but now it's used across types of extreme events. And this relies on observations to kind of measure how severe or extreme this event was, and then model setups like I described earlier to say, what would have happened then? What are we seeing now? What do we think we will see under potential future scenarios? So, we can't answer this question with a yes or no, but we have some kind of answer that we can give to it. And we're getting to the point where people will do attribution studies within just a couple of weeks of the event. So we're getting to where this answer comes pretty quickly. Okay. So I went into grad school thinking of atmospheric science as this confluence of things I liked. I had a background, very basic in severe weather, and otherwise basically knew nothing. I couldn't tell you the order of the layers of the atmosphere with any consistency. I didn't know what I was doing, but I was excited about everything. So when people pitched projects to me, I was like, yeah, that sounds cool. So I started studying winter weather in the North Atlantic region, and how different layers of the atmosphere impact that. So we need 2 layers of the atmosphere for this. We live down here in the troposphere, which goes up to about 10 kilometers on average above the surface. And lots of things happen in the troposphere. It's really exciting, right? We have land and ocean, and there are contrasts between them. We have topography, things are really bumpy. Storms bubble up all the time, all these waves. Troposphere, always something happening. Above that is the stratosphere, which goes up to about 50 kilometers or 30 miles. In contrast, the stratosphere is really stable and quiet, calm. Only a few things regularly happen in the stratosphere. And one of them is this feature over the winter pole called the stratospheric polar vortex. But it doesn't just kind of live there on its own, isolated from the rest of the atmosphere. Sometimes all of this activity in the troposphere sends waves kind of bubbling up that can disturb things in the stratosphere. So the troposphere can affect things higher up, and then when that happens, the stratosphere can affect things lower down in turn. And that's what I study. So the object I look at is the stratospheric polar vortex. So this is a graph. We're looking at east-west wind at about 30 kilometers up, the 10 hectopascal pressure level, on average over the year. So positive numbers are west to east. So you can see in the northern hemisphere from about September through April, we have these west-east winds around the pole, centered on 60 north. And there's a parallel structure in the southern hemisphere. That region of winds encircling the pole is the polar vortex. Inside of that, you have low pressure, really cold temperatures. And I guess the one other thing to notice here that I'll come back to is it's a lot stronger and longer lived in the southern hemisphere than in the northern hemisphere. So when I talk about weak vortex events later, these are mainly northern hemisphere events. It's a lot easier to disrupt our polar vortex than the southern hemispheres. And it's because of those things from the stratosphere coming down to the troposphere that we care about this, right? If this were just living on its own, 30 kilometers up, that's fine, it's interesting. Doesn't matter to what we do. But when the polar vortex is especially weak, we tend to get a cold and snowy area on the US East Coast, and then this cold, warm, dry, wet dipole in Europe. And when we have a strong polar vortex event, it's the opposite. So the best example of the weak one is in 2018, for folks that were in the Northeast then, we had about 4 nor'easters in 2 months. And that was following one of these weak vortex events. It was pretty directly attributable to it. Okay, so what do we know from theory? We know why the polar vortex forms. You can derive this basically from conservation of momentum, the ideal gas law, and then just thinking about how the sun's radiation changes throughout the year. And this feature pops up. We know the ingredients for weak and strong vortex events to occur. Someone named Matsuno came up with the theory for this in the 1980s. And basically it's these waves. If you have a lot of these large waves coming up from the troposphere, you're going to get a weaker vortex. And that tells us why the southern hemisphere vortex is so much stronger. These waves tend to be the result of land-ocean contrast and topography. And in the southern hemisphere, there's simply a lot less land. And so that vortex is a lot more symmetric and strong and long-lasting. But there's a lot that we don't know from theory. We really don't understand why disruptions to the polar vortex kind of come down, drift down back to us and affect our weather. We can't always figure out how this interacts with other phenomena in the atmosphere. So that's what we need observations and models for. So observing the stratosphere is a pretty recent thing. The first time the Arctic stratosphere was measured was with weather balloons in the 1940s, basically post-World War II. The first time someone saw one of these weak vortex events was in 1952. The scientist who got the measurements was extremely surprised because this didn't look like what the stratosphere was supposed to look like at that time of year. We got a lot more measurements in both the Arctic and the Antarctic during the International Geophysical Year in the late 50s. So that's when we first start having kind of consistent measurements of the polar stratosphere. I would say we don't have reliable ones until 1979, when we got more weather satellites with stratospheric sounding units on them, right? So 1979 to present, we have this kind of consistent set of observations that we believe. Before that, it's more patchwork. And if we think specifically about weak vortex events, what we know from observations is kind of that pattern I showed earlier. In terms of precipitation, in the 2 months following one of these events, we get a wet southern Europe and a dry northern Europe, and then this kind of dipole structure over both continents in terms of temperature. This is pretty consistent. So we definitely know this from observations. We can also make some other conjectures. Sorry, I'll come back to that. Like that something about the tropical Pacific seems to affect the polar vortex. So if the term El Nino and La Nina is familiar, in an El Nino year, it seems like the polar vortex tends to be weaker. And in a La Nina year, it seems like it tends to be stronger. But the number of these like particularly weak events where the vortex actually breaks down doesn't seem different between the two of them. But if we're working since 1979, we don't really have enough years to say this solidly from observations. This is when I'm going to go back and make a caveat about my use of the word observations. I've been lying to you a little bit, they're not really observations. They're what we call reanalysis, where basically we can take the strengths of observations and of models and combine them. And so what's great about observations is they measure what really happened. Ultimately, this is what we care about. But they're pretty irregular in space or time. They often come from a variety of sources that we're trying to patch together. And then there's some measurement error, right? And then models are great because they're true to our understanding of how the atmosphere works, right? How the fluid dynamics and heat transfer and thermo all work. And they give us uniform information everywhere, right? It's not, we only know at this point or at this point. So we can kind of put a model under observations to make this all more consistent. This is called data assimilation, and we use it to build these data sets called reanalyses. So basically, you can think about, we have an initial forecast in the blue, we get some observations, we wiggle our forecast around a little bit, and then we use the corrected one from there. We keep doing this process. So when I say observations about the polar vortex, basically always mean reanalysis. Okay, so back to the El Nino example. Right? Reanalysis just isn't long enough or reliable enough over the longer period to let us answer this from the observations. So this is a great place to experiment in a model. Right? I can set up kind of 3 parallel versions of the same model. One that always has an El Nino, one that always has a La Nina, and one where it's just neutral. Right? And I can run each one for 200 model years and see what happens to the polar vortex on average under each of those cases. What we tend to get, this is pretty consistent across model setups, is with El Nino, we do get a weaker polar vortex on average. With La Nina, we do get a stronger vortex on average. So that is consistent with what we thought we saw from observations. But the models behave really linearly. They say your polar vortex is weaker on average, you have more extremely weak events. Your vortex is stronger on average, you have fewer extremely weak events. And this is not really what we were seeing in the observations. So right now we're in a space where we're trying to figure out if the observations are just too short, it's noisy, we're not seeing the signal, or if there's model bias and the models are behaving too linearly. So folks are still trying to reconcile these. I reviewed a paper earlier this fall about exactly this question. So really active area that folks are trying to figure out. So to step back, right? We get information from and need all 3 of our tools. We need theory and conceptual models because having intuition and a broad understanding of what happens and why lets us do everything else. We need observations because that's ultimately what matters to us. We want to know what will and has actually happened. Right? Climate models let us make predictions, which are useful to people. And then they also let us do this flexible exploration, where maybe things are too complicated for theory and we don't have the observations to do what we need. And then all of these use math, right? Whenever we're thinking about modeling, whether that's theory or the climate models, we're doing translation of the physical world into mathematical descriptions. Whenever we're looking at results in some sense, whether that's from observations or the models, We're doing statistics with for our analysis. And then underlying these, we have things like all the numerics of working with the climate models, or the differential equations and probability that let us do data assimilation to build these reanalysis sets. Right? And then if we back all the way up, we're back at chaos theory, telling us why this is a hard problem in the first place. So I'll stop there. Thank y'all.
Cool. I think we have plenty of time for questions. I know I've got one, I've got many actually, so I'm going to be selfish here and grab the first one. Jessie, this was an awesome talk. I'm really glad to have gotten to see some of how you put together all of these different parts of climate science, especially organize them in your head. I have a question on the way you organize these different topics. So like this slide is an appropriate one to sit with. I feel like I've seen a similar slicing, at least within aerospace. We talk about like within fluids, there's sort of like the theory, the computational fluid mechanics part, and then the experimental fluid mechanics. So this feels very similar in character to me, to the way I guess fluid mechanicians divide their own discipline. But I'll confess, when I look at something like climate models, I think of that as just doing theory, but on a much larger scale. So how do you sort of articulate the boundary between those?
Yeah, I would say a lot of it comes down to the work people feel like they're doing. We don't have as many people actively working in the theory space anymore, but this looked like kind of a lot of pencil and paper first principles,
So
idolized
theory.
kind of work, right? Or like very basic tractable numerics.
Yeah.
Right? Whereas if I talk about someone as a modeler, I either mean that they're kind of doing this numerics and building out the models, or maybe figuring out some of the parameterizations for the things at grid scale that might cross these boundaries. But a lot of times what we feel like we have for theory there is pretty weak.
Okay.
And then other people might consider themselves modelers because they use models extensively. That's mostly where I live, right? I'm not building the models, right? I'm taking this mostly black box, reaching in and fiddling with knobs to do my experiments. And so I wouldn't really say that I live in theory land, right? I sometimes try to back out theory from results from the models, but this is where I live.
Okay. That helps. Thanks.
Okay. All the boundaries are fuzzy.
Fair.
Could you go into a little more detail on what reanalysis means? So I see you got observations, so I'll have like a temperature or pressure measurement. What does that mean when you get those measurements? What do you do with them?
Okay. In order to build reanalysis, or what do I do with
Yeah,
them?
when you describe reanalysis, just explain what that means a little more.
Okay. So this particular setup is what's called 4D VAR, 4D variational data assimilation. And the idea is basically that we're kind of correcting our initial conditions later to fit our observations better. Right? So we're starting with the model from what we think is the current truth. And then we're saying, oh, we were pretty far off. So I'm going to nudge my initial condition based on those observations to get the new one.
You're calibrating model parameters.
Yeah.
Got it. Okay.
The other way to do this is an ensemble Kalman filter. So basically, modeling centers are largely split between those two.
And do you usually not get an interpolation when you do this kind of assimilation? It's like, this is a cartoon picture right now.
Yeah.
I'm wondering, like, are these models, do they seem to indicate a strong lack of physics or bias in the predictions?
So I don't know that I have the strongest answer to that, but I can try. For the most part, when people do comparisons of reanalysis, so sort of our obs plus model, with more direct observational, not quite raw, but raw data sets, we tend to get pretty consistent results. And so people stick to the reanalysis because it gives us this kind of broader coverage. I know of a couple of areas where people have found disagreements. I'm thinking of maybe some circulation things near the tropics. And when they've dug in, what they found was that it was kind of a reanalysis problem, that the obs were more reliable in that case. But I don't know a ton about it.
Okay. And when you say consistency, do you mean, say, independent groups do a reanalysis on the same data set that come to the same sort of tweaked parameter sets?
Okay. So I guess, multiple things there. So yes, we have multiple groups using the same or similar observational sets with their own models, building out different reanalysis sets. So basically every modeling center also has their own reanalysis. But I also mean that there are some cases where we have kind of a dense and consistent enough observation set, if I'm looking at weather stations in Europe, right, that maybe I could use just that to try to come to conclusions about my question, and I can compare that to the conclusions I would come to if I were using various reanalysis.
I see. So you have something you can treat as ground truth for testing of the analysis.
When we're lucky, right?
When
In
lucky.
some places, in some cases.
Okay.
Yeah.
So you showed what the effects of the weak polar vortex were on the map. Why is that? What's the importance behind that in terms of just the study of weather in general?
Sure. Right. So I'm going to try to rephrase this question, and you can tell me if it's what you mean. Why should we care if we can say like the average weather pattern over the next 2 months? Right, so that's not as important to an individual, right, as maybe the weather forecast for today or tomorrow, but it can be really important to governments and industries, right? If we can tell the shipping industry or the agricultural industry at the beginning of winter that it's going to be colder and drier than normal, right, that might matter for them. If we can tell the airline industry that we expect a stronger than normal jet stream over the next couple of months, right? That has effects on their fuel use and timing. So kind of at larger scale levels, that's where these sub-seasonal and seasonal predictions matter.
So multi-million logistical questions.
Yes.
Multi-million-dollar logistical questions.
Yeah.
So you're collaborating with others outside. How big is the group that you're collaborating with?
So I've never worked in smaller than a trio. I've gone up to 5 or 6. That's the most you'll see on kind of basic science papers in my field. Review papers or things trying to evaluate new models, new reanalyses, those will be a lot larger. But most projects are a handful.
I've got more questions. So one of the things you mentioned using a model for is to assess this question of does something like climate change lead to more tropical storms? I'm wondering, with some of these global climate models, is a tropical storm or a hurricane a subgrid scale phenomenon?
So
Or does it like across a handful of cells.
Yeah, so that, let's see. You can probably run a full grid system model at a fine enough scale that it would cross grid scales. A lot of tropical cyclone studies are more regional scale models, and can get finer grids.
Okay, I see. So in that kind of model, you are actually resolving the vortex structure, and then for, I guess, is it just popping back out to setting boundary conditions for that regional model? And I guess, what do you get that from a global climate model, or?
Generally, yeah.
Okay.
Some people are starting to work on some, you would never do this for like how many storms are we getting, but for something like understanding surge of a particular storm, some people are starting to work with adaptive meshes, right, to maybe better resolve coastlines
Yeah.
in ways that might matter for storm surge. So, yeah, depending on the scale of the question, you can use a model at a different scale, and then you're bringing in information from larger or smaller scale models.
It's interesting. So like, the use of models is very extensive in this field. Like,
Yes. Yeah, honestly, this like theory model dichotomy is not really fair. There's kind of a hierarchy of models spanning that space that people work with.
Okay. But I guess it's safe to say that when it comes to that particular study of looking at number of storms that get generated under these different conditions, it's not like you're making all these assumptions about phenomena happening within one of these giant grid cells.
No, you would be doing something where you can actually resolve a storm.
Okay.
What's the size of a grid cell, I mean, typically that you're looking at? In miles?
So I do things that are typically 1 to